In this video, we'll cover the concept of stability of numerical solutions to differential equations. After studying this video, you should be able to identify whether a numerical solution is stable or unstable, and describe some of the factors that can affect the stability of a numerical solution. Recall that the error in a numerical solution to an initial value problem will grow with time as the local truncation error accumulates with each time step. So this is a review of the Euler's method video. But recall, as we go forward in time from some y0, we'll use the slope at y0 to predict y1, and use the slope at y1 to predict y2, and the slope at y2 to predict y3, and so on. As we move forward in time, the total error is growing with each step. And this is inevitable as we have errors due to the approximation in the method, the truncation error, that's going to add as we calculate y at each step forward in time. But what can happen sometimes is that this error grows really quickly, and that leads us to the idea of stability. A numerical solution is said to be unstable if the errors grow in an unbounded fashion as the solution progresses forward in time. What can happen here is that the error in an unstable solution can grow to overwhelm the solution itself. In other words, that total error as we move forward can be greater than y, even much greater than y, such that our numerical solution is worthless. So an unstable solution is no good, and we'd like to avoid that. Some factors that affect stability include the differential equation that's being solved. Some differential equations are ill-conditioned, and they'll result in errors that always grow regardless of the method. And there's nothing we can do about that except to hopefully find a method that works for at least the time span that we want before that error grows to be too large. Stability can also depend on the numerical method that we're using and the step size h. To get a little bit more insight into this concept of stability, let's look at applying Euler's method to the first order differential equation dy dt is equal to negative a times y. And in this differential equation, a is just some constant. So let's start by figuring out the analytical solution. So the analytical solution, or exact solution, we can get again by separation of variables. So we have dy over y is equal to negative a dt, integrating both sides from y0 to y, and from 0 to t, we get for the left side natural log of y over y0, and for the right side negative a times t, which we can then solve for y. Taking the exponential of both sides, we get y is equal to y0 e to the negative at. So there's our exact solution, and we can look at that exact solution and we can see that this is a decaying exponential function. So as t goes to infinity, we know that y should go to 0. So as far as the differential equation itself, a solution is inherently stable, since we would expect the errors to not grow in an unbounded fashion if the solution itself is heading towards 0. So let's look at what happens if we solve this with Euler's method. So to solve this with Euler's method, we would write the iteration scheme. yi plus 1 is equal to yi plus dy dt times h. And that dy dt is just going to be our function here. There's our function of t and y, although not a function of t in this case. So we get yi plus 1 is equal to yi plus negative a times yi times h, or yi times 1 minus ah. So we can call the factor 1 minus ah, that term, an amplification factor, because it describes how the previous value in the solution yi is amplified or scaled to get the next solution yi plus 1. For a stable solution, similar to the analytical solution, we know that we want the absolute value of yi plus 1 over yi. That should be decreasing as time goes forward. So the absolute value of y at the next time step divided by y at the previous time step should be less than 1. So that tells us that the absolute value of the amplification factor, 1 minus ah, should be less than 1. So solving for h in that case, that tells us that h should be less than or equal to 2 over a for a stable solution. So in other words, this gives us a criterion on the step size to make sure we have a solution that doesn't have errors growing in an unbounded fashion with time. If h was greater than 2 over a, then yi plus 1 would be greater than yi, and our numerical solution would be growing in time, and that would be because of the errors, as opposed to a solution that is decreasing with time, as we know from our analytical solution, that should be decreasing with time. So we would say that for this differential equation, Euler's method is stable, conditionally stable, and that stability depends on h. So let's look at this in a little bit more detail. So just because it's stable doesn't mean it's accurate. So here we'll look at the same differential equation, but now with a equal to 5, and I have a graph here showing the analytical solution. Y is equal to e to the negative 5x, y naught is equal to 1, and let's look at solving this by hand with Euler's method and a variety of step sizes. So let's start by taking h is equal to 0.1. So at h equals 0.1, we get yi plus 1 is equal to yi times 1 minus 0.5, or 5 times 0.1, or yi plus 1 is equal to yi over 2. So we can look at what that solution looks like. We do see that y will be decreasing with each step. And the first step will just go at that initial slope down to y over 2, or 0.5. The next step will go to 0.25. The next step will go to 0.125, and so on. And we do see a numerical solution that's stable and approaching 0, decaying exactly like the analytical solution. That said, we do have errors. So it's not necessarily accurate. And we know from previous discussion that we could increase the accuracy by reducing the step size h, or by going to a more accurate method that we will talk about, a variety of more accurate methods in future videos. But here we just want to look at how does the stability depend on the step size. So for h equals 0.1, we get a numerical solution that reflects the decaying behavior of the analytical solution, and it is stable. Now let's try a solution for h equals 0.2. So for h equals 0.2, we have yi plus 1 is equal to yi times 1 minus, now 5 times 0.2 is just going to be 1, or y plus 1 is equal to 0. So for h equals 0.2, we get a numerical solution that goes from y naught equals 1 directly to y1 equals 0, and then it will stay at 0 going forward in time. So here again, with the green solution, we have a stable solution, but not so accurate. But that solution does still represent a solution that reflects the characteristics of the analytical solution, notably that it decays as we go forward in time and it approaches 0 as time approaches infinity. So let's go one more step. H equals 0.3. If h equals 0.3, we get y I plus 1 is equal to yi times 1 minus 1.5. So we actually get negative 1 minus 1.5, or negative 0.5 yi. So in this case, we're going to get a solution that goes at 0.3. We're going to still follow that same initial slope, but we're going to follow it all the way down, since h equals 0.3, down to negative 0.5. And then for our next solution, we will go again, negative 0.5 times negative 0.5 gives us a positive 0.25. So we would go right here, and we would keep going down like so. So we see with the red solution, or our h equals 0.3 solution, we see some oscillations in the solution, which are often an indication of instability, but it is still stable. And again, it's stable now because the error is not growing in an unbounded fashion. Clearly, it's not accurate, and it's not reflective of the true solution. We know that true solution does not exhibit any oscillations about 0, but here with h equals 0.3, we do get oscillations. So we know that that's not reflective of the true solution. Step forward again, h equals 0.4, one larger step size. Plugging that in, we'll get yi plus 1 is equal to negative 1 times yi. So our h equals 0.4 solution has even greater oscillations, basically going back and forth between 1 and negative 1. So again, the error is not growing in time. So for h equals 0.4, we would again say it's stable, but definitely not accurate. And the shape of the numerical solution is not reflective of the exact solution. So finally, let's go to h equals 0.5, and at h equals 0.5, we get yi plus 1 is equal to negative 1.5 times yi. Now note here, h equals 0.4. Remember, our stability criterion was that we wanted h to be less than or equal to 2 over a, or h less than or equal to 2 over 5, or h less than or equal to 0.4, which is 2 over 5. So this solution at h equals 0.4 is right at our stability criterion. Any h is smaller than that, we get a stable solution, which is what we've seen. So an h larger than that, we would expect an unstable solution. And we see that's what we get. You can look here and you can see with each successive time step, yi plus 1 is getting larger. And so this is going to look like, we're going to take that all the way down to negative 1.5, and as we go back up, we are getting an unstable solution. The error is growing forward, growing large as we move forward in time, as just getting to y2, so y1 would be equal to negative 1.5 times 1. y2 would be negative 1.5 times negative 1.5, or 2.25. By our second time step, already our numerical value y2, this is greater than twice our initial condition. So it's growing. This would be unbounded growth of the error in a way that the error now in the solution is overwhelming the solution itself. So again, that h equals 0.5 case, that's going to be our unstable case, and any larger values of h are just going to make this even worse. So we'll come back to this concept of stability several times as we move forward in our study of differential equation solvers. It's not always this easy to kind of analyze how a method's going to behave, because as we look at more complex methods, we won't be able to solve them by hand. However, the same general concept applies where a lot of methods are stable conditional on the step size, and that's what this example illustrates.